All right. Hess's law basically says that the enthalpies of individual reactions equal the enthalpy of a total reaction if we add the reactions together. It's easiest just to kind of jump in and we'll show you what we mean. So, how to find delta H by adding reactions. All elements, first of all, in their standard state have a delta H equal to 0. So in other words, hydrogen, H2, in its standard state, it's a gas. If I look at it on the periodic table, so its delta H is 0. That's the heat of formation for that. All right, bromine, its standard state is liquid. So if we have liquid bromine, its delta H is 0. Iron, it's a solid in its standard, its natural state. So it's 0 if we have just iron. And generally the disclaimer here too is that these things are at 25 degrees Celsius and 1 atm. Okay. We can write the formation of several compounds from their elements. This is called the heat of formation and is symbolized by delta H sub F standard state. This stands for standard conditions. When you see this, the degree sign written with a symbol like this, and you're going to see it with enthalpy and then two other things, entropy and Gibbs free energy. All right, and you will see that in later chapters. The F stands for formation, and the degree sign stands for standard conditions. Okay, what does this mean? Well, if I write, first of all, delta H is per mole of a substance. So if I write just the equation for the formation of NaCl, so I take Na plus Cl2, and then if Na is a solid in standard conditions, Cl2 is a gas, and I form NaCl, which is also a solid, and I balance that, and I get a 2 here and a 2 here. However, that means that 2 moles of this react with 1 mole of this to form 2 moles of this. Well, delta H's are only reported for 1 mole. So the heat of formation reaction for NaCl, we have to reduce the NaCl to 1, and then this becomes 1/2, and this becomes 1. And I know you can't balance equations from 1/2, but this is what I'm just showing you what the delta H means. So now the delta H for this, the energy for this whole process to happen, the energy exchange is negative 411 kilojoules per mole. And so that means that this is an exothermic reaction. Energy is given off in this formation, and it is this amount. If we do the same thing for glucose, in glucose's case, we take carbon, we take hydrogen, we take oxygen, we add them all together, and we get glucose. But then, of course, we have to balance this. This is a solid. We have to balance this, and to balance it, we got to put a 6 here, and a 6 here, and a 3 here. And these are all in their standard states, so they're 0. But the whole formation of this is negative 1,275 kilojoules per mole. It's very exothermic, again. So that's just the basic idea of where the energies come from when we use them in equations. So let's move on to the next page. To find the delta H by using reactions and adding them together, you must, number 1, add the source reactions such that they cancel out to get the reaction you are looking for. When you multiply a source reaction, the value of delta H for the reaction is multiplied by the same factor. When you reverse a reaction, the sign of delta H is switched. These are just general rules, and really just jumping in is what has to happen to understand these, and you'll do that with your line kappa. Sometimes it is easier to multiply the main reaction by a factor and then work the problem. If you do this, you must then divide the delta H of the reaction by that same factor at the end, and you'll see that eventually. Okay, so calculate the enthalpy for the combustion of carbon to carbon monoxide. So carbon, adding it to oxygen to carbon monoxide, and they want to know the delta H. Well, this is a two-step process. There are two reactions we can look at to do this. One is carbon plus oxygen yields CO2, and the delta H for that reaction is negative 393.5. And then the second one is carbon monoxide, because we don't want to produce CO2, we want to produce carbon monoxide, but we can use this reaction also, which also produces CO2. And we have to somehow manipulate these reactions and then therefore manipulate these values to get this reaction. So what does that mean? Well, we have one carbon on our final reaction. We have one carbon atom. This reaction is the only one that has a carbon atom, and it is in the right spot. It's a reactant. We've got oxygen here. We've got oxygen here. So I'm happy so far. We've got carbon monoxide here. We don't have CO2 here, but let's see what we can do with this. We don't have CO on the reactant side, but we have it on the product side, and that's where we want it. So if we flip this equation and we make it CO2, and then if we have to flip this also. All right, so now if we, so I'm going to cross this out, so we're just looking at these two equations. And we can, if we were to add these two equations together, some things would cancel. That would cancel with that. This wouldn't cancel with anything. But we have one O2 here. We have half an O2 on the other side here. So we can make this 1/2 O2. Now, when we add these two reactions then together, we're going to get C plus 1/2 O2 yields CO, and remember this canceled. So that yields CO, which is the reaction that we are trying to get. Now, to find the delta H, we simply have to add up our final enthalpies for the two reactions we were working with. So the delta H, remember we changed this to a positive sign when we switched it. So delta H is going to be negative 393.5 kilojoules plus 283 kilojoules. And that's going to equal negative 110.5 kilojoules. And it is per 1 mole. We made 1 mole. That is the enthalpy. It's a negative enthalpy. This is an exothermic reaction. Okay, next one. I want you to give the next one a try at home right now, and then we'll go over this one in class. I'll tell you, though, that the final answer will be, let me see if I can find it. The final answer is going to be okay. Moving on. All right, Hess's Law version 2 works with reactions also, but it's probably the easiest one. And basically, you just sum the products, or you sum up the enthalpies from, and you can look those up in 821 in the back of your book. And so this means sum of, so you sum of the enthalpies of the products, subtract sum of the enthalpies of the reactants, and you get your answer. So again, let's see. We'll start with this one. If we look in the book, and usually a lot of times you're given this. Sometimes you're given part of them and you're given the final answer and you have to find them. All right, and then HCl is negative 92. I'm not going to write the units with it because I'm running out of room. NH4Cl is negative 314. So I'm going to take the sum of my products, which is negative 314 because I only have one product. And I'm just going to subtract from it the sum of my reactants. And hey, I should have made sure this was balanced. I think it is. It is. All right, so it's going to be negative 46 plus negative 92, and you do that calculation, and you're going to find that the delta H equals negative 176 kilojoules per mole. All right, and the next one, remember you can look on H21 in the back of your book for this. I want you to try this one, and we will go over it in class. If you have questions, the final answer is negative 2046 kilojoules per mole. Okay. The last method is calculating